Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 11 on partitioning the hypotenuse with an altitude. That sounds fun. Anyway, this is kind of a fancy way of talking about something, so let's get into it because what we're talking about here is not all that tricky. Let's talk about what an altitude drawn to the hypotenuse even means. A very special case of similarity arises when we draw the altitude from the right angle vertex of a right triangle to the opposite side, which will always be the hypotenuse of the right triangle. This altitude partitions the hypotenuse in a very specific way. In other words, it divides it into two segments in a very specific way, all due to similarity. All right? So let's kind of jump in and sort of understand where similarity even comes in. Exercise number 1. Right triangle ABC is shown below with angle ABC as its right angle. The altitude from BD to the hypotenuse AC has been drawn. It is known that angle BAD equals 55 degrees is marked. And I apologize, it really should say right here the altitude from B to AC. It's not from BD. The altitude is BD. The altitude from B to hypotenuse AC has been drawn. All right, that altitude is BD, but it's not from BD. Anyway, it's known that angle BAD is 55 degrees as marked. Now, before we even move on, I just want to give nod to something. The original right triangle, the large one, ABC, right, is lying on its hypotenuse, which is a bit weird, but in a lot of these problems, that's sort of the way that they're oriented. Not in all of them, but in many of them. Now, letter A. How many right triangles are in the diagram? Write their names below. All right, we'll pause the video right now. Use your eyes and tell me, how many right triangles do you see? Well, in fact, there's 3 of them, right? There's the big one, ABC. There's the medium-sized one, BDC. And then there's a small one, ADB, right? So we've got triangle, there's 3 of them. We've got triangle ABC, that's our original one. We've got triangle BDC, and we've got triangle ADB. And let me put that extra right angle in there so it's really kind of clear that, okay, that one is a right triangle as well. Now letter B. Fill in the measures of all acute angles in the diagram. All right, so let me be very clear. We have this acute angle, this 90-degree angle. There's an acute angle here, an acute angle there, and an acute angle there. All of which you can fill in by using the fact that the acute angles of a right triangle are always complementary. In other words, the acute angle right up here is just going to be 90 minus 55, right? This acute angle over here is also going to be 90 minus this 55 because it's part of this right triangle, etc. So pause the video now and go ahead and fill in those angles. All right, well, if I just consider right triangle ADB, right, this guy right here, I can do 90 minus 55 and I'll find that angle is 35 degrees. Now, likewise, right, if I wanted to figure out this angle, I could always say, well, this entire angle is equal to 90, so 90 minus 35 would be 55 degrees. That doesn't really look like 35, so I'm going to write that a bit better. Maybe a little arrow there. 35 degrees right up there. Now, to figure out what this angle is, I could always do 90 minus this angle, and that would be 35 degrees. So it looks like in this diagram, I either have 55-degree angles, 35-degree angles, or 90-degree angles. Letter C. Why can we say that all of the right triangles from A are similar? Well, we can say it based on the angle-angle similarity theorem, right? Whether we're talking about this small right triangle compared to the medium one, they both have 55 and 35-degree angles, or whether we're talking about any one of them and the large right triangle, which has angles of 55 and 35, right? All 3 triangles are similar because they have the same angles, right? So we could say it by the angle-angle theorem. And again, they don't just have two angles the same. They have all three angles the same. I just, for some reason, don't want the red this time. All right. Now, when I wrote the triangles up here, I just was randomly kind of writing them down. But now we really kind of want to see which ones correspond with which by really kind of having them all look the same. I'm going to draw that. I'm going to put in those 35 and 55 degree angles again right here. All right. Now let's take a look at letter D. Draw the two smaller right triangles in the same orientation as the larger one, then write a similarity statement being careful to make sure corresponding vertices are in the correct order. All right, so in this particular problem, right, what I can see is that my large right triangle is lying on its hypotenuse, okay, with the shorter leg sort of tilting down this way and the longer leg stretching out that way. I want to draw this triangle and this triangle in the same orientation. So I'm going to draw sort of a smaller version, and I'm going to draw maybe a slightly larger version. All right, and I'm going to be putting that right angle up at the top because that's where it is there. Now, if I just hone in on the smaller one, right, the A, which is the 55 degrees, has to be the angle that's sitting right here, right? So that's literally got to be A. And I'm going to throw the 55 degrees right in there. Now, its right angle, which is sitting right here at letter D, has to be sort of, if you will, at the top of the triangle. And then the 35 degree angle, which on that particular triangle corresponds to B, whereas the overall triangle it corresponds to C, that has to be right there. All right. See if you can pause the video right now and label the medium-sized triangle, if you will. Now again, right, on the medium-sized triangle, the 55 degrees corresponds to B. All right, its right angle is at D, and its 35 degree angle is at C. So now we've got all three of the triangles oriented in the same way. I can now have a similarity statement. I can say, and I'll start with the big one first, triangle ABC is similar to triangle ADB, which is similar to triangle BDC. Right? So ABC, ADB, BDC. And of course, all of this is necessary to be able to do if I'm then to go on and start to set up proportions and solve for side lengths. Guess what we're going to do next? Let's keep going. All right. Now, in general, anytime the altitude is drawn from the right angle vertex to the hypotenuse, three similar right triangles are created. Anytime, okay? And it doesn't really matter how they're oriented. So let's take a look in exercise 2, where we have the original right triangle oriented in a more kind of standard way. Exercise 2. In the diagram below triangle EFG, the altitude GH has been drawn to hypotenuse EF. It is known that EH is equal to 2 and HF is equal to 8. Letter A. Mark all congruent acute angles in the diagram. All right, now we're going to do this a bunch, okay? And the reason we're going to do it is it's going to help us then kind of orient the triangles properly. So this is what I always do when I have a situation like this. I pick one of the two acute angles in the large triangle and I mark it with a single arc and a dash through it like that. All right? Then I take the other acute angle in the larger triangle and I mark it with an arc with two dashes. I like to use the dashes here instead of the double arcs for a reason that you'll see in a moment. Now what I'm going to do is I'm going to go into the smaller right triangles, the two smaller ones, And whatever the acute angles are that are left over, I'm going to mark them with the other one. So in this smaller one, right, I've got an arc that's a single arc mark, right? This one then has to be the double. And when I go into this one, because I already have one with a double, this one's got to be the single. All right? In other words, this angle is equivalent to that one, and this angle is congruent to that one. All right? And if you really want to put in a nice touch, maybe throw in that last 90-degree angle so you can kind of see them all. Now let's take a look at letter B. Draw the two smaller right triangles below the larger one, but in the same orientation. Okay, so keep in mind, right, in the large right triangle, kind of almost try to ignore this, right? I've got, right, my single arc mark, my right angle, and my double arc mark. So I want that exact same orientation with my small right triangle and my medium one. So let me put sort of a smaller one, and then the medium one. All right, and again, I want it to be this way. And I'll throw my right angles in as well, just to have them. Okay, now, take my small triangle, right? What letter is sitting by the single arc mark? Well, that's letter E, right? What letter is sitting by the right angle? That's H. What letter is sitting by the double arc mark? And that's G. So that now is my small right triangle drawn in the same orientation as my larger one. Now let's go for the medium one. What letter is sitting by the single arc? That's G, right? What letter is sitting by the right angle? That's H. And what letter is sitting by the double arc? And that's F. And now my medium right triangle is drawn in the same orientation as my large one. And again, the reason to do this is it's going to make it much simpler to say, well, this side corresponds with this side corresponds with this side, etc. Okay, now let's look at letter C. Use similarity of the two smaller triangles to determine the length of GH. So keep in mind, right, all three of these triangles are similar to each other. So let's just look at the two smaller ones and the information they've given me. Right now I know EH is equal to 2 and HF is equal to 8. So let's try to get that on here. EH is equal to 2, HF is equal to 8. All right, and I think that's what I got. I'm going to put it all also up here. 2, HF is equal to 8, right? And now, somehow, even though I just got a side here and a side here, I have enough to figure out GH. Why do I have enough to figure out GH? Well, notice, and I'm going to like highlight this really quick with a highlighter, right? Here's GH here. And here's GH here. You see the key is that GH is part of both of them, right? It's here and it's here. So I can now say 2 divided by GH, right? 2 divided by GH is equal to GH divided by 8. Right? And all I'm doing, right, is doing what we've done throughout this unit. This length divided by this length is equal to this length divided by this length. Probably the biggest difference here is that the length I'm actually trying to find is part of both of the two ratios, right? And now I can just cross multiply and I'll get GH quantity squared is equal to 16. Easy enough. And now I'll take the square root of both sides and I'll get GH must be equal to 4. Okay, it's as easy as that. Let's take a look at letter D. I want to keep all three of these things in my view. Letter D. Use similarity of the smaller right triangle with the original to find the length of GE. Express your answer in simplest radical form. All right, so here's something that's going to get messy. I'm going to see if I can get rid of this highlighting for right now so that we can go back to the original. Now I'm looking for GE. So yet again, let me highlight some things. All right, I want to really kind of highlight what I'm looking for. I'm looking for GE, and I want that, and I want my smaller right triangle, and there's GE again, right? Notice the thing that I'm trying to solve for here, at least in both of these two particular problems, is part of both of those triangles. I should probably go back and grab my pen so that I'm not writing in a highlighter. All right, so now what can I do, right? Well, I don't know the length of EG, but it's the hypotenuse of my small triangle, and I do know the length of that short side of my short triangle. And then I've got my larger triangle, and I'm looking for its short side, but I do know the length of its hypotenuse. Granted, I know how its hypotenuse got divided up, but I can, of course, add those two together and get 10. So now what I could say, right, again, trying to keep that in, is I could say GE divided by 2 is equal to 10 divided by GE. All right, and again, I have to kind of keep it like this in order to really talk about it, but GE divided by 2 is equal to 10 divided by GE, right? And now, just like before, we can cross multiply. We'll get GE squared is equal to 20. 20 is not a nice perfect square, unlike 16 was. So I'd have to break that into the square root of 4 times the square root of 5. And that's 2 times the square root of 5. And that's it. Now, what makes these problems especially challenging, right, is the fact that the triangles that are similar, and there's 3 of them, are all kind of in these different orientations, right? Problems involving this type of similarity can be challenging because the 3 right triangles are all oriented differently. They're all different, right? So it's kind of hard to see which side corresponds with which side. The key will always be to understanding which sides correspond to which, and those angles can help us. So let's take a look at exercise number 3. In the diagram of right triangle RST, altitude RU is drawn to hypotenuse ST as shown. Mark all congruent acute angles on the diagram. All right, so just like before, I start this problem by immediately going into it and going, okay, well, I'm gonna put a single arc with a dash on T. I'm going to then put a arc with 2 dashes on S. That means this has got to be a 2, and this has got to be a 1, and I'll even throw this extra right angle in there. Again, this helps me think about how to orient things, and we're going to do that in letter B now. Draw the 2 smaller right triangles in the same orientation as triangle RST. Use part A to help. All right, well, we've done this a couple times now, so I'd like you to pause the video and see if you can draw the 2 smaller right triangles, obviously the small one and the medium one, in exactly the same orientation as triangle RST, and then label their vertices. All right, well, notice the larger right triangle, right, has its right angle at the top and then the 2 acute angles at the bottom. So I'm going to draw sort of the smaller version of that, and I'll just immediately do that. And then I'll draw the medium version of it, and I'll do this, okay, right? Now, keep in mind, right, that I also want that single arc on the left and the double arc on the right. So I'm going to be looking at this, and this, this, and this, okay? And now I'm just going to hone in on my small one. T goes beside the single arc, R goes beside the double arc, and U is at the right angle. On my median triangle, R goes at the single arc, U is again at the right angle, and S goes at the double arc. And now I've got them, right? All 3 of my triangles are oriented in exactly the same way. Now let's take a look at letter C. If RU is 10, and TU is 5, find the length of SU. All right, let's start to label things. Now, I'm gonna label these two lengths everywhere I can. RU is 10, so there's a 10, there's a 10, and there's a 10. RU is showing up everywhere here. TU, that's 5, and that's 5, right? But I don't see it anywhere on my medium triangle. And I want the length of SU, and that one I'm gonna highlight just to kind of distinguish it. Let's see, I've got SU here. All right, and I've got SU here. Okay, and that's what I'm looking to find. Now, right, notice that SU is not a segment length of the larger right triangle, right? It's part of a segment, right? But it's not actually one of the three sides. So then I take a look at my two smaller triangles, right? Here I've got my 5 and my 10 and SU, right? Here I can now set up a proportion that I can solve. All right, so let me get my pen back, right? And now it should be easy because I can literally say 5 is to 10 as 10 is to SU. And again, let's talk about this a little bit because there's lots of 5s and 10s rolling around. 5 is to 10 as 10 is to SU, right? So this one divided by this one equals this one divided by this one. We can now do a little cross multiplication and we'll get 5 times SU is equal to 100. Divide both sides by 5 and we get SU is equal to 20. All right. One of the tricky things about all of these is it's hard to know, at least when you first begin this work, which two triangles you're going to use to set up your proportion. Am I going to use the small one and the overall large one? Am I going to use the small one and the medium one like I did here? Am I going to use the medium one and the large one, right? Which two am I going to have to use? And that's all about having the three triangles drawn in similar orientations, labeling all the lengths you know, and then really understanding the length that you want, right? And where it occurs. All right, now sometimes you will be asked to solve problems involving these types of triangles without ever being given an image to work with. Carefully draw a good diagram using everything given in the problem. So let's take a look at exercise 4 for an example of that. In triangle MNP, where angle P is a right angle, the altitude PL is drawn to hypotenuse MN. If ML is 9, LN is 3, then find the length of PN. Okay, so this is much more difficult because they have not given me the picture. So I'm going to have to draw one, and I better make it good, right? So I'm going to draw the overall large triangle. Now, the first thing I really have to know in my overall large triangle is where the right angle is. It's triangle MNP, P is the right angle. Right there. That means I can put M and N, right, in either one of the sides. It doesn't matter. This doesn't have to necessarily be perfect, right? And now my altitude is drawn. What is my altitude? Well, it's PL. Okay, so now I've got my picture. Maybe I'll throw in my right angle, and now I'm going to start to throw in my acute angle markings. Okay, I'm going to single, double, single, double. Okay, so I've got that all set, right? Now, before I even start to put down any measurements, I'm going to draw my other two triangles in the exact same orientation as my large one. Right, I got my medium and my small, and again, the way this should work out is single, double, single, double, right angle, right? What does my small one look like? It's got an L there, an M there, and a P there. My medium one has got my L here, my P here, and my N here. And now I've got all three triangles. They're not drawn beautifully, but they are drawn in the same orientation. So now let's start labeling lengths. We know that ML is equal to 9. On the big triangle, that's just this length. All right. On my smaller triangles, it's right here, but it's nowhere on my medium-sized one. I know LN is 3, so this might be a little bit not to scale, but that's okay. I can deal with it. LN is 3. Okay. And I want to know the length of PN. All right, let me get my marker. So I want to know the length of PN. PN is right here, and PN is right there. All right, and let me just switch back to my pen. All right, now, it's a little bit tricky, right? Because I don't know much about my small triangle, okay? What I do notice is that the segment that I'm looking for is a side on my large triangle, and it's a side on my medium triangle. So in all likelihood, these are the two I'm using. Now, there is one thing that I don't quite have on my large triangle, right? I've got that length measured, which is 9, or marked, sorry. I've got that line marked, which is 3, but I should really also note that overall, that's equal to 12, right? Now, why is that important? Well, it's important because I can now say 12 divided by PN is equal to PN divided by 3, right? So I can set up that ratio. 12 divided by PN is equal to PN divided by 3. And that will not be unusual when the side length that you're solving for occurs in the two triangles, right, that you're trying to use to set up the proportion. I now cross multiply. I get PN squared is equal to 3 times 12, which is 36. And I take the square root of both sides, and PN, what I'm looking for, is equal to 6. All right. This is definitely one of the trickier applications of similarity. We're actually going to spend 2 days on it, and in our next lesson, we're going to introduce something called a geometric mean. And that may or may not make these problems a bit easier, but ultimately, right, again, these are all about drawing out similar triangles and seeing what proportion you can set up to solve for whatever side you're missing. All right, let's take a look at one last problem. Now, similarity through transformations. Recall that two figures will be similar only if a similarity transformation exists that will map one figure onto another figure. Since these problems involve 3 similar right triangles, the ones we've been working on, those mappings must exist. In other words, there's got to be some similarity transformation, and recall, a similarity transformation is a dilation along with as many rigid motions like rotations, translations, and reflections that you need to get the figure to map on itself. One dilation and some rigid motions, right? And given that these 3 right triangles are similar to each other, there's got to be a similarity transformation that would map each one of them to the other one, each one to the other one. So let's just take a look at one of those as our final problem. Exercise number 5. In the diagram shown below, altitude GH has been drawn from point G to hypotenuse EF. Mark all congruent angles in the acute angles in the diagram. All right, well, we've done this a ton. Pause the video now and go ahead and do that. All right, well, again, what I'm getting at here is just, we got this thing, I'll go like that. This, I'll go like this. This one, I'm going to go like this, and that one, I'm going to go like that. Okay, great. Now, letter B, right? Draw triangle EHF on tracing paper. Use this to verify that EHG, I don't know why I said EHF. Draw a triangle EHG on tracing paper. Use this drawing to verify that EHG shares the same angles as GHF. All right, well, we already kind of know it does. I've already drawn it out on tracing paper, okay? But if we want to, what I could do is I could take this triangle. It's a little bit tricky. I could kind of orient it like this, and here it shares that angle, here it shares that angle, and here it shares that angle. It'd be great if I could have just like somehow, and now I want to orient it back again, if I could have brought those arc marks along with it, but not so simple. All right, but it definitely matches them all up, right? So they've got to be similar because they have the same angles. And now let's see if we can figure out that similarity transform. Letter C. Describe a similarity transformation that would map triangle EHG onto triangle GHF. Be as specific as possible. All right, this is also where that tracing paper will help you quite a bit. Now there's gonna be multiple ones, all right? See what you can figure out. Pause the video now and see if you can figure out a combination of a dilation along with one or more rigid motions that will map the smaller right triangle onto the medium one. All right, well the first thing I'm gonna do is I'm gonna take this smaller one and I'm gonna rotate it by 90 degrees counterclockwise so that it looks like that. All right, that's the first thing I'm gonna do because I love it when the picture looks like that. All right, so I'm going to, let me extend my page a little bit. I'm going to rotate triangle EHG by 90 degrees counterclockwise about point H, right? And again, the great thing that will happen in that case is obviously this ray will lie along here. This ray will lie along there because of that 90-degree angle. Now the key is I just need to stretch this thing out, right, so that that vertex ends up there and that vertex ends up there. Keep in mind, right, at this point, this is sort of E prime, right, and this is G prime. All right, so now what do I want to do, right? I want to dilate it at this point. So I'm going to dilate triangle E prime, H prime, G prime, all right, with a center at H. And then what should my scaling constant be? Well, I already know that the two triangles are similar by the angle-angle theorem. So my scaling constant simply needs to be the ratio of any image length divided by the pre-image length. So one thing I could do is divide GF by E prime G prime, which is the same as EG. Or I could do HG divided by HE. Or I could do HF divided by HG. Any of those would work. I kind of like the two that are parallel right here. So I'm going to say with a scale factor, remember it should always be image divided by pre-image. So I'm going to do GF divided by EG. And that will then stretch it out so that it maps on top. All right, let's summarize. What we saw today is one of the most peculiar and specific examples of similarity. Specifically, when you have a right triangle and you draw the altitude from the right angle to its hypotenuse, that altitude then partitions the hypotenuse in such a way that three similar right triangles exist. All right? Those three right triangles can then be used along with proportions, right? Along with, proportions of, corresponding sides to solve for missing sides in this scenario, all right? The most challenging thing about these problems is that the three right triangles are all oriented differently. And what's very helpful whenever you're trying to solve these problems is to redraw the two smaller triangles, smaller one and the medium one as I like to call them, in the same orientation as the largest triangle. That can be aided by marking off the acute angles and understanding where your acute angle pairs are congruent. All right. Once you've got those triangles drawn in that way, then you just have to label lengths that you know, highlight the length that you want to find, set up a proportion that will allow you to solve for those missing lengths. We're going to do this a bit more in our next lesson when we introduce the idea of a geometric mean. But for now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.